Hi, stats people from the very sunny but also very blizzard warning of New Jersey. And so, as a funny aside, I will note that I turned off the cat water fountain just for this video, and my cats are irritated at me. So, just for you guys, no water running in the background, but no guarantee you won't hear cats meowing about it in the meantime. So, let's talk about chi-square. So chi-square is going to be a switch from a lot of the things we've been doing this semester because it's a non-parametric test. So chi-square really should be called kind of nominal data tests. And so just kind of a reminder of where we started this semester. So parametric tests like ANOVA, T, and regression are used when that dependent variable is continuous. So really you can have categorical IVs or continuous IVs for ANOVA and regression, but the DV had to be continuous. Now, when we use chi-square, it's a non-parametric test, which you will love here in a minute because it has very little data screening. Woohoo! So things like chi-square, proportion tests, log regression, they're used when that dependent variable is not continuous. Mostly when the dependent variable is nominal. We can work with some ordinal data, meaning it's ranked, but there are also other ordinal analyses that you can do. So kind of the way I'm going to break down this section is talk about chi-square globally and then work my way through each of these. So it focuses on the number of people in a different category. So we've got these categories. It's a nominal thing, either yes or no, or it could be any set of types of categories that you're interested in. And that really breaks down into two types of chi-square. So they either have one variable that they're interested in, and that's generally either a proportion test or goodness of fit test, most commonly goodness of fit, or they have multiple variables that they're interested in. So we're going to just stick with two. We're looking at a chi-square independence test, Fisher's exact test, or McNemar's test. So I'm going to talk about each one of these, with the caveat that proportion tests usually are only interested in one variable with two different groups of people, but it's actually two variables kind of reduced into one. So let's start there. So for our one variable test, we can look at proportion tests. Now, I've seen a lot of these in athletic training literature that people have asked me about. And what it does, sometimes it's called a prop test, is it takes two independent proportions. So what do I mean by that? It means two entirely different groups of people and the same proportion that you're interested in. So the example I pulled from just Googling proportion return to play was looking at soccer injuries. So if I compare men and women, do they have the same percent return to play? We could also think about this as just two different groups of people who have the same percent of something happening. Now, really, that is really a 2 by 2, meaning that I have my two different groups of people, men and women or whatever, and then a sort of a yes or a no variable as my other variable. But I'm really only interested in one of the proportions. Because if you think about it, if I have 50% of people return to play, that means 50% of people don't. So it tends to be considered a one variable test because you're just testing if two groups of people have the same proportion on one variable, but that means they have the opposite proportion on the other half of the variable. There's also McNemar's is also considered a proportion test, but we're going to talk about it in the section about two variables because that's how more commonly it's reported. But McNemar's allows you to determine if two dependent proportions are different. And so McNemar's is a repeated measures test. And all the rest of these are independent tests, but McNemar's is the only repeated measures chi-square, where you have people sort of tested on two different variables, and they can be in multiple boxes. So one of the big rules on chi-square it's not really a data screening test, it's just one of the rules is that I can only be in one category. McNemar's I'm allowed to be in multiple categories. So, in theory, proportion tests can also be considered two variable chi-square as sort of usually considered a 2 by 2, meaning I have two different groups or two different test times for McNemar's, and I have two different categories. I'm just calculating the proportions. Okay. Also in proportion tests, let's say you have 3 different categories. So you were testing if the percent of, here's a popular problem in Missouri, the percent of racial minorities, are those equal for all the different universities in the state. So I could compare if our proportion is equal to, let's say, Mizzou's proportion. Obviously, there's more than 2 categories that I could have for racial minorities, but I'm still reducing that down to comparing 2 proportions at once. So proportion test can actually be a double chi-square or a 2-variable chi-square. It's just people they're only interested in maybe one little piece of that chi-square. Okay. So to get into the rest of chi-square analyses, I want to kind of define a little bit of some terms. So the first one is observed frequency. Observed frequency is really easy. It's just the number of people actually in that cell. And these don't have to be people. They could be mice, they could be rats, they could be how many times you hear the cat in the video. It could be anything, but it's the number of things actually found in a cell. So that's why it's not considered a continuous variable, is because these are frequency counts. Frequency counts tend to be kind of classified as something else. And so we're not averaging these, we're just taking the total number of counts. The expected frequency is the number of people that you'd expect in a cell if the null was true. Now that can be kind of tricky. So what basically an expected frequency is just the number of people you'd expect if everybody was equal. And that depends on what type of test you're running. But when you see it up here in the formula, know that that's what I would expect if everybody were equal. Okay, or every category were equal. So a 1-variable test, the other 1-variable test is a goodness of fit chi-square. And so that just tells me how well observed frequency distribution of one variable fits some expected frequency distribution. Okay? So how well those observed values fit some expected values. And if you want this to be significant, you want them to not fit the expected values. Sometimes we don't want them to be significant. So for example, let's say we're comparing, one of my students on her thesis this semester was pulling men and women. So she was looking at the number of men and women who either participated in the study or weren't in the study. And we were hoping that those would be equal. So we're looking at the frequency distribution of men and women in the study and the frequency distribution of men and women outside the study. Okay. That's technically a 2-variable test, but it's kind of that idea of seeing if that pattern matched the expected frequency. On to the 2-variable test, and we'll do examples of each of these. The first one is the independence test. This is the most common type of chi-square. Unfortunately, people tend to call goodness of fit and independence test just chi-square, blanket term. So when you see someone say chi-square, you're never quite sure which one they did. You have to figure out how many variables they had. So an independence test looks at the distributions of frequencies for one variable related to another variable. If it's a 2x2, meaning I have 2 categories of one and 2 categories of other, it's actually considered kind of like a correlation. But what independence tests do is they allow me to see if there's an interaction between these 2 variables. And I know that's everybody's favorite term right now after ANOVA is interactions, but it allows me to look at if the pattern of rows is the same for all columns, or conversely, if the pattern of columns is the same for all rows. So it's not just that I expect everyone to be equal. I expect all of these to be equal given how many people are in each row and column. And this will make a little more sense when we put some numbers to this. But it is a test for independent data only. Just like a goodness of fit test is for independent data only, I can only be in one box. So no matter how many different category options there are, I can only be in one of them. Another type of 2-variable test is Fisher's exact. Fisher's exact is actually really useful. It doesn't work out so well in the example I have, but it's really useful if you have a very small sample size. So it's actually got the exact same definition as the independence test because Fisher's exact is an independence test. So the question is, how is this different? Why would I use it? So what chi-square does is when you calculate chi-square, it uses an approximation for that p-value. So we calculate how different the observed and expected values are from each other. And then it approximates the probability of getting that difference. Fisher's exact, hence the name, calculates the exact p-value. So what it does in the background is takes every possible combination of your frequency tables, so the possible observed values, it calculates every possible combination of those, and then sees how many times your option came up. Fisher's exact will only work for very small studies, meaning it has only a couple of categories for rows and columns. And so the example that we have online, it'll do a 2x2, a 2x3, and a 3x3. If you get much larger than that, the whole thing will crash your computer because it's calculating exact p, which is an iterative process, so it has to calculate every possible combination of your design. And chi-square is much better. Now, when you do Fisher's exact, it actually is a much better test when you have a small frequency. So not only do you need a small number of possible categories, the frequency in those cells works much better if it's a small frequency. Because then it's easier to calculate all the possible combinations because there are less of them. Now, chi-square is a better test overall, unless your n is small. So if your sample size is small and your design is small, Fisher's exact is better. If your sample size is large, chi-square works just as well. Okay. The last one is McNemar's test again, and it actually is a two-variable test, but it's for dependent data. And usually it's used as a dependent proportion test, but it's kind of both. So you'll see McNemar's and they might talk about proportions, and then you'll see McNemar's and they might talk about just a 2x2 chi-square. And I just wanted you to know that that's the same thing. It just depends on the goal of the researcher which way they report it. We're going to kind of lean towards proportions, but they're mathematically the same thing. So let's start let's back up and talk about what is chi-square actually doing. So it calculates this observed frequency distribution. So here's O here, your actual values in your study. And then you calculate your expected frequency distribution, and that depends on the type of test you're running. And from that, we can get the chi-square statistic. So all year we've been talking about good variance to bad variance, or a ratio of the odds of your study to error. Essentially, this is the same ratio. So believe it or not, everything that you were doing with ANOVA is a different type of chi-square. So ANOVA is actually like two chi-squares at once. Because the F distribution reduces down to a chi-square distribution, but that is beside the point. Generally, we're interested in, is the observed value different from the expected value? However, if we add all these up, they add up to 0, just like the problems that we have with standard deviation. So we're going to square that bad boy, because we like squared things, and chi-square is, squared. So that is our difference score. It's just like ANOVA's, where we're taking the differences between means, just like t-test, where it's mean 1 minus mean 2. So this is the same idea, divided by error. So our expected values. So for each one, we're creating a difference from expected. Okay, and then we add all that up. The chi-square distribution looks a little like this. So we can have a bunch of different degrees of freedom. And so generally, with smaller degrees of freedom, now degrees of freedom has 0 to do with the number of people in your study, and it varies by test type. So I'm going to talk about degrees of freedom as we go through examples, but it's unrelated to, and I'm just going to put that here, unrelated to sample size. DF is based on number of categories. And I'm going to spell unrelated correctly. There we go. So it's not based on the number of people in your study, it's based on the number of categories you have. And so just kind of an example of what chi-square looks like. Okay. So the logic of a chi-square, if it is a non-significant test, you would not reject the null. P is greater than 0.05, if you will. I would expect all of the frequencies, my observed frequencies, to be equal to my expected frequencies. So O and E are 0, essentially. So O minus E is 0 on the top, and it doesn't matter what the error on the bottom is. If it's significant, I expect my observed frequencies to be different from the expected frequencies. So they can be smaller or they can be larger. The whole thing is squared, so it doesn't matter which direction. But O minus E is some number larger than 0. So I have a large number on the top to a small number on the bottom. Remember, all statistical tests are some sort of ratio of things that happen in the study to error, and we want those ratios to be large because that means something happened in our study. Often you don't want significant chi-squares because maybe you're testing, like I can give the example of my student study, the distribution of men and women, but if I did want that to be significant, I want that to be a really large ratio. So you guys are like this. Data screening for chi-square is kind of glorious because it's a non-parametric test. So parametric tests, which take up the majority of this class, are actually pain because they require all these rules. It's got to be normal, it's got to be linear, it's got to be homogeneic, homoscedastic. It has to have additivity, like rule after rule after rule. Non-parametric tests don't really have those rules because there's no way for categorical variables to be normal. They are this or that, and we're counting how many times it is this or that. So it doesn't tend to have the same rules. So kind of two big rules. First is that each person is in their own square for the independence tests. Anytime it's a dependent test, I can be in more than one square. But for the everything but McNemars, I am only in one proportion or one square. Then I just need to make sure that data is accurate, so I don't have any weird typos or anything. And the main one is the observed frequency for each cell. Okay. So you shouldn't really have very many small frequencies. Less than 5 is sort of the rule for small frequencies. And you'll actually see that some of the calculators we're going to use online will actually not run if you have a lot of cells that are less than 5. I always get the question of how many cells can be less than 5. I've seen it should be 20% of the data or less, meaning 80% of the data needs to have at least 5 people per cell. There's no hard and fast rule on that one that I've seen. That's the most common rule I've seen. So 20% of the cells or less should... Well, that's hard to say. Okay, let's put it the other way. 80% of the cells should have at least 5 people in them, okay? Which means that 20% can have less than 5. Okay. And you should not have any zeros. Okay. Fisher's exact is the only exclusion to this rule, which is meant for small frequencies and zeros. Okay. So if those two conditions are not met, you should use Fisher's exact if you can, or combine categories when you can. It makes sense to combine into one larger group, or get more data. So this is not a good analysis for very small samples. Fishers can work well with very small samples, but in general, most chi-squares do not run well on small samples. Okay. And that's true of any analysis, remembering that we want our samples to be larger to be more precise. So let's say I give you a big ass data set in Excel and it's just a bunch of words and you weren't given the raw numbers. Now every other example we're about to work, you're going to have the raw numbers, but let's say you don't have the raw numbers. What is a quick and easy way to get those raw numbers? Now if you've been using R all semester, you can use the table function. There's some ways, a couple of little ways to do this in JASP, but it's not very easy. Honestly, Excel is the easiest way to get these sorts of numbers using pivot tables. So the more things you're going to learn in Excel this semester. So I've got a big data set from, I don't even remember when, book example of whether or not people had all these different phone services. I don't even remember where I got this. So I have just categorical variables. So this is a good way to know there are no numbers here. Now I could make them numbers, 0 and 1. But I don't need to in this case. I could rather leave them as the category labels themselves so I remember what's happening. So let's say I want to create a pivot table of this data. Click on Insert, and then Pivot Table. Okay. It's going to pick the whole data, that's fine, and I'm going to stick this in a new worksheet. Now, pivot tables are really cool because they allow you to do all kinds of things. You don't even have, you can use these for means and stuff as well, but I find it works better, a little bit better if you're doing categorical variables, but anyway, so let's pick two of these. Let's look at education levels. So I'm going to drag education level down here to row. Well, I'm going to try. And what that does is it shows me all the possible options out here. And then let's see if internet. I'm going to drag internet, good grief, over here to columns. And so it's going to show me the number of people who are at this education level who have the internet. At the moment, there are no numbers in here though. So I'm going to take internet down here. I'm going to drag it also to values. And then my automatic option is count. If you click on the little I button, you can actually see standard deviation, mean, min, max. This is another way to get descriptives for 2x2s, but it was not nearly as easy as just like throwing that into JASP. So, or using R if you were using that. So this gives me my frequency table. Let me blow this up so I can show you. Move this thing over here. So I can see, okay, I have, for people who have a college degree, there's more people in the yes category, so this gives me the total going across here. Did not complete high school is almost no one has the internet, and it kind of looks like it goes up for the other degrees. Post-undergraduate degree, there's not very many people, but there are way more people in the yes category. And then you can make this actually as complicated as you want. So you could actually do add customer category over here. I'm going to take it out of here. So I can look at how many people use the internet based on also this customer category. So they get kind of complicated, but you can make tables that are split in multiple ways. And the nice thing is that I can turn things on and off. So let's say I didn't mean to do that, I can turn it off and go back to my original one. So that is how I can use pivot tables to get these frequency counts rather than just like trying to count. So let's do a proportion test. So I pulled this from a sports injury magazine, and they were looking at, this is the direct quote, and then I pulled these numbers from a table. The men were more likely than women to say that their injury was the primary reason they were no longer playing soccer. And they gave a p-value here. We're going to test and see if that's right. With a forewarning that it's probably not correct. So I can use this link here to go directly to the prop test. Or what we're going to do is use VassarStats website. VassarStats is one of my absolute favorite websites when it comes to doing statistics on the internet. They got some cool stuff in here. So to get there without clicking on the direct link, we can click on proportions. And there are a couple of different ones, but we want here the significance of the difference between two independent proportions. And see, here's McNemar's test. And the nice thing is it gives you some explanation here. They also have a whole book too, but I would fill in the numbers that I had. So K of A. K is the number of people that have the thing that you're interested in. So I would say 31 out of 55. So click here, 31 out of 55. K of B is 12 out of 45 from their study. And then I just hit calculate. It calculates the probability of A, so that's where the 56 came from, and the probability of B, which is 27. Did my best to make the math work. And this is just a subtraction of those two. Here's our z-test here. So this is a z-score test. It's in the chi-square section though because it is actually technically a chi-square. and gives me my probability. So we want to use this two-tailed probability over here. So I cut and pasted that output over here, and I pulled z from here. So z equals 2.98, p equals 0.003. So this would be a significant difference in probabilities between 56 and 27-ish. So nice and easy. It's one thing I like about VassarStats is it's very clear and easy. All right, a goodness of fit test. Remember, this is one row of data or one variable. So I found this data a couple of years ago, so I don't remember if I am in this data or not. But I teach Psych 200, and we always get this perception that our class is easy. So is there a difference in the number of A grades for each of the same undergraduate, and this really shouldn't say psychology, this should say statistics courses. So Psych 200, Soci 302, and Math 340 are technically all the same course. There's also a QBA one, but I couldn't find those numbers. And so if a student takes one of them, they can't take the other ones. They're all the same thing. And we get this perception that ours is the easiest one, so people should take ours. And if I just look at these raw numbers, we do have the largest number of students in the A category. We also have very large enrollments, so that might be due to that fact. But let's just compare these three and see if there's a difference across these three courses in the number of A's. So we're going to go to a goodness of fit test, which I would click on frequency data, unless you want to use the direct link. I'm going to scroll down, and it says chi-square goodness of fit right here in the middle. Now on this one, what we have to do is come up with our expected proportions. So I'm going to do 25, 18, and 11, pulled from here. And remember that expected proportion is as if everyone were equal. So what I'm going to do is I'm going to take 25 plus 18 plus 11, and I'm going to get 54. So the total in is 54. If everyone were equal, they would all score the exact same. We would have an equal number of people in each class. So I'm going to divide that by 3, and I'm going to get 18. So this expected frequency here is just if in a perfect world everyone were equal, we'd get the same number of A's in each course. So the summary of that is add them up, divide by the number of categories. And then hit calculate. And it gives you a whole bunch of stuff out here, which we're going to look at on this slide here, so all at once. So it says that it's not significant, but it's close. So when you enter those expected frequencies, it calculates the expected proportion, which just says that each one should be about a third. And then it tells you I had 54 total over here. And here's the chi-square stuff down here. So chi-square is 5.44. Our p-value is 0.07. And our degrees of freedom is 2. Okay. So where do we get df from? So df here is just the number of categories minus 1. That is not an e. There we go. So it calculated 1, 2, 3 categories, 3 different courses, minus 1. Okay. What would you do if it was significant? So let's say P was less than 0.05 here. What I would do is I'd look at standardized residuals. So standardized residuals come up right here in this column. And what they are is it's a z-score, or similar to a z-score, of the difference from expected. And so the difference from expected divided by expected added up is chi-square out here. So it's not like I added these two up and got 5.44. That mathematically does not add up. So what's happening here is it's sort of a standardized difference from the expected. How would I determine if those were different from what I would expect? And most people use plus and minus a score of 1.96. 1.96 or 2, generally you'll see listed 2, is a z-score where it's p less than 0.05. So you can kind of think of standardized residuals as a post hoc test. And what it does is it allows me to show which cells were different from expected. So chi-square is kind of an omnibus test where I'm showing that overall the observed values do not match the expected values. And here it's close, so p equals 0.07. And then I would say, okay, which ones are different from observed? And then could pick out and say, the first class, which is Psych 200, has more than expected because its value is positive. It's a little bigger. The second class has right at the number of expected, which is SOCI 302, I think. And this last class has less than expected, which is the math version. But none of these are significant, so it would need to be 1.96 because 1.96 is a z-score of p less than 0.05. So it still matches our big important rule. Let's do that. All right. So goodness of fit test, I have one variable. So it only really allows you to type in one variable, and you do have to come up with the expected frequencies. Remember to do the expected frequencies, add them all up, divide by the number of categories. So let me talk about phi for a second. Sometimes people just say v, but it's technically phi. And there's another little symbol for it. Most people use the uppercase Greek letter. But it's an effect size for chi-square test for independence. Okay, so we're about to do an independence test, and the effect size for that is phi. And what you do is you take that chi-square value, divide by n, this is total sample size, and then divide by and times the degrees of freedom smaller. Okay. So the way that you calculate this, it's the smaller number of either rows minus 1 or columns minus 1. Okay. So rows minus 1 or columns minus 1 to make that a little clearer. So let's say you have a 2 by 3. So I have 2 rows and 3 columns. 2 minus 1 is 1, 3 minus 1 is 2, so you would go with 1 there. Okay. Now this is going to be auto-calculated for you, but I think it helps to see like what the heck it is. And then because we love size rules, so we've done Cohen's d of 2.2, 0.5, 0.8. We've done eta squared of the square of R1. So R, correlation coefficient, is 0.1, 0.3, 0.5. That should look real familiar right here because they're the same. If I square those for R squared, I got 0.01, 0.09, 0.25. Okay. And so these are actually the same as a single r, lowercase r. And what that does is it's because if there are only 2, row or column, then it actually matches the correlation coefficient. Okay, so I got 0.1, 0.3, 0.5. If I have more degrees of freedom, I have other rules. Also from Cohen. He was busy doing effect sizes. So let's do an example. Let's take that exact same question of statistics courses, and let's look at 3 professors. So okay, I'm going to take Psych 200 because this is the easiest class, and let's look at ABC categories and then compare our 3 professors. So this is actually real data, and I don't remember who is who in this particular set of data, but the Student Government Association used to print these numbers, and they don't anymore, and I don't remember why, but you could actually look people up by ABCs and by the professor. And I'm going to plug that into an independence test. What would that answer for me? What that's going to tell me is if the pattern of A's is different across professors than the pattern of B's and patterns of C's. So are the patterns of the columns different by rows? Or are the patterns of rows, is professors 1's ABC different than professors 2 ABC? So it's actually looking for an interaction. So the way to get there is to click on frequency data and then come down here, and it's not a goodness of fit test. We're going to click on chi-square, Kramer's V, and lambda. Okay. And so this is a 3 by 3. Okay, so I have 3 rows and 3 columns. And we're going to fill in 5, 6, 5, 12, 4, 3. So I'm going to do 5, 6, 5, and 12, 4, 3, and then 11, 9, 3. and hit calculate. So it'll calculate those totals, row totals and column totals for you. And we'll scroll down a little bit and we'll look at this thing here. Now, it tells me that it's pretty unhappy with me because at least 80% of the cells must have an expected frequency of 5 or greater, and no cell may have an expected frequency smaller than 1. So it's actually calculating the expected frequencies for me, but it's pretty unhappy with the number of cells here that are so small. So it didn't want to do this chi-square, but it still gave it to me. Now, where did this degrees of freedom 4 come from? Well, the way that's calculated, we'll come over here, and I'll add that to my list here, is that df is rows minus 1 times columns minus 1. Okay. And so it got 4 by taking 3 minus 1 times 3 minus 1. So 2 times 2 is 4. And I would fill in my numbers here. So it's not a significant test. So our p-value is greater than 0.05. But here's how we write chi-square, 4 degrees of freedom, 4.82. V here is 0.2. So it calculated that number for me. And if I back up a little bit, 0.2 is somewhere between small and medium. Let's see, 0.2 degrees of freedom, smaller is 2. Remember that this table here is for degrees of freedom, whichever is smaller, rows minus 1 times or columns minus 1. So it's actually a medium-sized correlation. And so it's a medium effect size. Even though it's not significant, the person might consider taking the professors with the more scores towards A and B, which might be Professor 2 here. Now, how could I follow this test up if I were interested in the, if it was significant and I was interested in the, which cells were bigger or smaller? On VassarStats website, it gives me percent deviation. I'm actually more interested in standardized residuals right here. So I could look at which residuals were higher or lower, right, than expected. The one thing I don't like about this is it doesn't show you the expected values. You can calculate them yourself, but it at least gives me these residuals. So I know that the expected value here for this A1 is lower than expected, and A2 here is higher than expected. So there are less A's in this spot and more A's than expected here. Professor 1 has more in the C category, whereas the other two have less in the C category. Okay. So that's how you'd read that. And then it gives a whole explanation of like exactly how this is calculated, so it's a z-value, and how all of this works. Okay. But remember the rule is 1.96. And so that's how we could follow up, is we could look at these standardized residuals and see which ones are greater than 1.96 positive or less than negative 1.96 as significantly different from their expected values. So you always have to talk about it as they're different from their expected values. So they're higher than expected or lower than expected. Now expected values for this type of test are calculated, back up 2 or 3 slides here, based on totals. So the expected value for this box, this 5 box here, is based on the fact that there's 16 Professor 1 students and 28 A's. So it's based on both row and column totals, not the entire table's totals, right? So it's if Professor 1 just had less students in their class, which they do, it biases that number a little lower because there's less people to work with. So expected values are calculated by using both row and column totals. All right, the exact same problem, but with Fisher's exact this time. So one of the issues we have with this test is there are several cells with 5 or lower. So we should be able to maybe use Fisher's exact to solve that problem, because it gave me the very grumpy, like, ugh, why? You shouldn't have done that over here. So to get to Fisher's exact, we can click on frequency data, and there's several versions of it. So it starts here. Version 1, if you have a 2 by 2, because we're not doing odds risk ratios in this video, that's in one of the other blocks. Or if you have bigger than a 2 by 2, this version of Fisher's exact. So I'm going to click on 3 by 3. And we're going to calculate the exact same statistic, but this time using Fisher's exact. So we're going to do 5, 6, 5, 12, I don't remember, forgot it already, 4, 3, and 11, 9, 3. And then we're going to click calculate. It's going to give us two numbers here. So it did not actually run the chi-square test because it said that you shouldn't. And they give you probability A and probability B. We want to use probability B. Whoops, I don't know what just happened. Okay. Here. And it shows you that on the notes. It says use probability B. So probability B is the likelihood of getting this set of data or smaller. So it's this set of data smaller than this set of data, like the likelihood of getting something this crazy or smaller. Probability A says the probability of getting this exact piece of data, which generally null hypothesis testing you want to use probability B. And they explain it a lot more up here, but it's the likelihood of getting only smaller. This one is equal to or smaller. Most people stick the equals in the null, so we're going to go with probability B. But it is also not significant. So that didn't really help us much. It's not chi-square is just non-powerful in this case. It's that chi-square and Fisher's exact pretty much agree. Oftentimes they will disagree when it's close to significant, okay? Because Fisher's exact has more power, meaning it's easier to find that result that you're looking for. Okay. However, almost none of the tests will give you a chi-square value. It'll give you just the p-value. So you would just list p here. And then it also does not give you any sort of effect size, which makes me crazy, but you would just list the p-value. Okay, let's end with McNemar's and then power. So for McNemar's test, this is correlated correlations, or sometimes considered repeated measures data. So I pulled this from a anesthesia study with words I could pronounce. So what happened was they looked at people, like kids, looking at who were undergoing surgery, and they were just having them answer whether or not they were scared. Now they did this in a more continuous way, but I sort of made up the data to match. And let's say before the study, they just asked them, how scared are you about the surgery and all of the stuff. And so this pre-score here over here is they were either pre-yes or pre-no. Okay. And then how many times were you, and then after they gave them a little intervention, like here's what's going to happen and here's what the doctor's going to do. And then asked them again, okay, now how are you scared? And so post yes and no. And what we're really interested in is the off, what's called the off diagonal here. And you'll see this as we enter it online, but we're really kind of hoping that everybody moves to this no category, right? So if they were pre-no and now they're post-scared, that's not good. These people, we didn't change their minds, right? And these people, we didn't change their minds. So this is sort of a considered match, right? Match. And we're really interested in the non-match, so the off-diagonal. This is also used a lot when people are talking about predictive validity of tests, but we're going to move that and talk about that sort of thing in one of the other clinical blocks. So let's get to McNemar's here. It's actually under proportions and frequency data because it's kind of both. So let's scroll down, click on the very bottom, McNemar's. There's a whole bunch of explanation up here too. If you aren't getting what I'm saying, you can look at what they're saying. But I think this is the most important part. What it does is it actually calculates the probability of sort of A, given A here, going across this row, and then the probability of B, but now going down. So really what we're comparing is B versus C, the off diagonals here. But the way that you do that is you calculate the probability of A plus B over the total, and then the probability of A plus C over the total. And that way you're controlling for the fact that this is repeated measures. So A is in there both times because we've got a control for those people. All right, really easy to enter here. So let's go back, let's get our data. We got 15 to 35 and 4 to 40. So 15 to 35, 4 to 40. Okay, and it would be inappropriate to compare these using a proportion test because they're the same people. Okay. People in A are the same people as the people in B. So we couldn't use our independent proportion test. Now there are dependent proportion tests, but it's the exact same test as this one. So we're just going to hit calculate here and get some totals. So it's going to give me those two probabilities. And I'm totally interested in those. More interested in the effect here, right? The other thing that you can really include is the ratio of discordant cells. Discordant cells, which means it's giving you the odds ratio of the off diagonal. So it's literally 35 divided by 4, so that odds ratio is very large. So people changed their answers in A in the first condition way more than they changed their answers in the second condition. So these are the mismatch pieces. So that's the odds of A1, B0, or going from, in our example, pre-yes to post-no, which is what you want. So they get less, they move to not scared, compared to the odds of pre-no to post-yes, which is not what you want because then you scared them. So it's almost 9 to 1. It also includes that confidence interval of those odds ratios, which is really nice. So it's a really big range because we just don't have a large sample. So how would I report McNemar's here? I'd list my p-value because it doesn't give you a chi-square test. But then you could also list the odds ratio. So remember, odds ratios are just the odds here of change for the first group to change for the second group. And you can interpret that the same way we can interpret a lot of our other statistics. It's a ratio of change for one group to a ratio of change for the other group. Now, last but not least is power. So when we're looking at power for chi-square, it kind of can be a little tricky, but because you don't want to have cells that end up being too small. And sometimes beforehand you just don't know that the cells are going to be that small. But there's an option here to click on chi-square test. And you have a couple of options. Goodness of fits test or a one sample case. And we really want kind of goodness of fit test. You can click determine. And there's a whole bunch of stuff I can calculate. So I could actually calculate the goodness of fit test because it pulls the effect size up here as W. But if I just hover over this, it's a little easier. And you'll notice that W here looks a whole lot like phi because it effectively is. Okay. So we can pick small, medium, and large here. So let's just pick a small one. Alpha is still 0.05, power is still 0.8. Degrees of freedom, we already talked about how to calculate. Right, so let's say we're talking about our first test, which is 3 minus 1, so it's 2. Hit enter. For a small effect size, I would need 964 participants, which is kind of a lot. If I change that to a medium effect size, I only need 108 participants. So that's one kind of quick way to do chi-square. You can also click on exact tests, and there are some proportion tests. So you can look at, here's McNemar's test, here's Fisher's test, and they have similar types of fields. So I could click on two tails. We've got odds ratio here for McNemar's. So let's do 8.75 because that's the giant thing we got. 0.05, 0.8. And the proportion of discordant pairs. You won't really know that before. So you can leave it at 0.3 as a good estimate. Right? It says I need 40 people. Fisher's exact test has a same type of thing. So it's our two proportion test for this one. There aren't very many good options in here. If you ask me what I'm going to do, I'm going to use this chi-square goodness of fit one and just estimate based on my degrees of freedom and my effect size. That doesn't totally get at the independence test, but it'll give you something close enough. Now for all of this, is there a picture? Because we always end with power and pictures. And in this case, not really. Most people list this data in the table, usually a table of either standardized residuals or tables just like these of the frequency charts, or they list out all the frequencies in the text.